Hello and welcome to session 3 of Unit 3. This session would introduce you to nuclear binding energy calculations in nuclear chemistry. By the end of this session, you should be able to do simple calculations involving nuclear binding energy. Let us look at binding energy. As discussed earlier, when a given nucleus is formed from 8 constituent nucleons, we know nucleons are made up of protons and neutrons. Enormous amount of energy is released due to the loss of mass during the process. And this explains why a heavy nuclei like radium, thorium, and uranium could split into lighter one or lighter nucleus such as hydrogen, lithium could be fused to form heavier nuclei with a release of a large amount of energy. The greater the binding energy per nucleon of a nucleus, the more stable that nucleus is. And so those nucleuses that are highly unstable and they can undergo radioactivity, their nucleon has less binding energy. The most stable nuclei are those having the greatest binding energy per nucleon, as we said. Now, there are some conventional factors that we need to know when it comes to nuclear binding energy calculations in nuclear reactions. Example, 1 mega electrovolt. 1 mega electrovolt is equivalent to 1.602 times 10 to the power negative 13 joules. Also, 1 atomic mass unit, 1 AMU, is equivalent to 1.661 times 10 to the power negative 27 kilogram. And also, 1 atomic mass unit is also equivalent to 931 mega electrovolts. We can also calculate the binding energy per atom in a simple manner by simply multiplying the change in mass or the mass defect, which we normally calculate in atomic mass unit, by 931.5 mega electrovolts per every atom. And this will give us binding energy, which will be in mega electrovolts. Let us look at some examples. Example 1 says that the mass of chlorine 35 is 34.9800 AMU. The mass of proton is 1.007825 AMU, and that of neutron is 1.008665 AMU. Calculate the binding energy per nucleon of the chlorine atom, and we should take 1 AMU to be 931 mega electrovolts. So let's look at the solution. To solve this problem, first of all, we find the number of protons in the chlorine, and we have 17 protons in the chlorine. 17 protons. The number of neutrons, which we are not given, but we can get it by subtracting the proton number from the mass number, and when you do that correctly, you get 18 protons, 18 neutrons, then we have been given the mass of proton to be 1.007825 AMU, and the mass of neutron also as 1.008665 AMU. So we can use this to calculate the mass defect, and from there we calculate the binding energy. First of all, we need to find the sum of the mass of the nucleon. Then, because we already know the mass of the atom, we can subtract to get the mass change or the mass defect. Now, the mass of the nucleon is given by the number of protons times the mass of proton plus number of neutrons times the mass of neutron. So this will give us 17, because there are 17 protons, 17 times the mass of proton plus 18 times the mass of neutron, and that will give us 35.2890 AMU. We have been given the actual mass of the atom to be 34.980. So to calculate the mass change or mass defect, we subtract the 34.980 from the mass of the nucleon, and that will give us 0.309 AMU. But we've been told that 1 AMU is equivalent to 1 AMU is equivalent to 931.5 mega electrovolts. If that is the case, then we can use ratio and proportion to calculate the binding energy in mega electrovolts. If 1 AMU is equivalent to 1.5 mega electron volt. Then 0.309 will be equivalent to what mega electron volt. And when you simplify, you get 0.309 multiplying 931.5, and that will give you 287.83 mega electron volt. And this is the binding energy. So these are self-assessment questions which I want you to try your hands on it.